All right, in this video, we are going to look at maximizing projectile motion functions, maximizing functions in economics, and also maximizing area functions. So in your guided notes, I want you to look at page 291, and there should be a blank space kind of in the middle of the page where you could copy this information down if you would like to. But the objective is to be given a real-world situation that can be modeled by a quadratic function and then use that information so we can talk about minimum values and maximum values. Mainly maximum values we're going to look at. So in section 4.1 we talked about the vertex pretty heavily, and we know that this is the x value where the vertex is located, and once I find that value I can substitute it into my function to find either the minimum value or the maximum value. So this actually should say maximum and not minimum. So that should say maximum. And our objective is to, one, determine if the situation either models this scenario where we're looking for the minimum or this scenario where we're looking for the maximum. And so we'll kind of discuss how we can determine that and what in our examples. In our first example, here we have a function that models the height of a rocket after it's been launched after a certain height. And so here I'll let you read that information, but we want to be able to answer two questions. How long after launch did it take the rocket to reach its maximum height? And what is the maximum height obtained by the rocket? And both of those questions are pertaining to the vertex. How long indicates a time. So we want to figure out a time t did it take for it to reach its highest point, and then what is the actual highest point the rocket reached at that highest point. So that's just utilizing that formula that we talked about in section 4.1, and also how we can find the vertex. So we know a couple things here. Because the leading coefficient is negative, that means that my parabola is going to open downward. So it's going to create a U that opens downward, and that means the maximum value is going to be at the vertex. And in order for me to find the vertex, I can do it one of two ways. I can actually graph this in the calculator or Desmos and then figure out what the highest peak is. Because I remember I want to answer two questions. I want to figure out how long did it take to reach maximum height. So that's a time. And then what was the maximum height? So after I figure out that time, I can substitute it into my equation and calculate that maximum height. So we know that we're going to have to utilize the formula that we talked about in section 4.1, which is to find the location of where the vertex is. And so here I'm using t instead of x, but t equals the opposite of b divided by 2a. So in my quadratic function here, I should be able to pick out the value of b, which is 44.1, and the value of a, which is negative 4.9. And so I know that that information, if I substitute it back into my formula and evaluate it, that's going to give me the x value essentially, or in this case the t value where the maximum occurs. So it takes 4.5 seconds for the rocket to reach its maximum height. And then how do I find that maximum height? Well, I can take that 4.5 and I can substitute it back into my equation and then evaluate it. So if I do that, it's essentially just taking that 4.5 and that's now my value of t, and that's going to give me the location or the height that the maximum rocket actually reached. So it's going to take 4.5 seconds for the rocket to reach a maximum height of 100.225 meters. And so here we have a second example we can look at, kind of similar, projectile motion. And again, I'll have you read this information here, but this is the graph of that. It's also given to you on page 292. And so in this situation, we're told a couple different things. The object is launched from a platform at a certain angle of inclination, at a certain speed or velocity, in this case 60 feet per second. And this is just the trajectory. So it was launched off the ground, and then it hits the ground finally after 120 feet from the target. And this is the function that models that trajectory. And so what we would like to determine is several things on page 292. There's actually three parts. In the first part, we want to figure out what is the height of the object when the horizontal distance from the platform is 20 feet. So here, my X variable, that's my horizontal distance, and my vertical height is the Y variable. So I want to determine, well, where is the location above the ground of my object when it's 20 feet from the platform? So just utilizing the graph, if I go over to 20 feet here, I can determine that the height of that object is somewhere between 20 and 30 feet. Now it's not halfway, it looks like a little more than halfway, so I can't just say 25 feet, but I can utilize my function here, my quadratic function, because I know that X represents the horizontal distance. If I go back, X is the horizontal distance the object is from the platform. Since I know the horizontal distance is 20 feet, well, I can just take that 20 feet and I can substitute it into the value of X here and the value of X here, and I can evaluate. So when I do that, H of 20, so I replaced X with the 20 here and here, I get approximately 26.44 feet. And so it wants us to round to 2 decimal places, and that I believe the actual distance, it gives us a little more information than that, but we don't need all the digits, we just need 2 decimal places. And so we can confirm by looking at the graph here of that trajectory that this is close, or this is correct, because it is between 20 and 30, but it's a little more than halfway between 20 and 30. Our second question now wants to know, what is the horizontal distance from the platform when the object reached its maximum height? So we have to consider maximum height. What is it referring to? What is the problem talking about? So if I want the maximum height, if I go over to my parabola here, well, I know the maximum height is probably going to be somewhere around here. That looks like the highest peak. So I want to be able to find 2 things. I want to be able to find that distance, the actual distance, and I want to be able to find the actual maximum height. I want to find those 2 things. So I know that this point on my graph is called the vertex. And because that's the vertex, then I can use that formula that we talked about, which is X equals the opposite of B divided by 2A, and that will give me the X value of the vertex. So in this case, it will give me the horizontal distance. And once I know that horizontal distance, I can substitute that back into my equation here, and I can then find the height. And so I would be able to answer both parts B and part C. So when I evaluate this, so X equals the opposite of B, so in my quadratic function, B is 1, divided by 2 times A, and A is this rational number, 32 over 60 squared. And when we evaluate that in that calculator, we get 56.25 feet. And so that should match what we looked at before, which the maximum height occurs at a horizontal distance between 50 and 60 feet. So that's my maximum height. And then, I mean, that's the location of where the maximum height occurs. And then, well, my vertical height is going to be evaluated at that number. So now I want to take this number and substitute it in for X to get the vertical height. And so that's the third part. You know, what is the maximum height of the object? So when I take that value we found previously and I substitute it in for my X value in those 2 places, remember X is here and here, then I can calculate the maximum height of the object, which is around 38.125 feet. And so that should make sense, because I go up to my function. It's not quite 40, just a little bit below 40, but I can't just say, hey, that might be 39, because of course your homework won't like that. So you want to make sure you utilize your quadratic function. So that's kind of our second example. There is a third example that I want you to look at, but I'm going to ask the questions in the video for that one. So now let's look at maximizing functions in economics. We talk about profit and revenue. And you have a little tiny space where you can write this kind of down at the very top of page 293. So dollar amount received by selling X items at a price of P is called revenue. And that revenue can be modeled by this function here, where X is the number of items you sell and P is the price for those items. Some things that we need to realize is that as the quantity of X increases, the price tends to decrease. And so this price is going to be a separate function that you're going to be given, and it's going to be situational. So it's going to represent whatever situation that we're referring to, and we'll look at that in a couple different examples. So the more items that we have to sell, the price tends to decrease. The fewer items that we have to sell, the price tends to increase, and that goes with supply and demand. Also, you might want to write this down in that same spot where it asks about revenue. Profit is described as revenue minus cost. And so if we kind of write that in a function notation form, profit can be modeled as P of X, generally capital P, not to be confused with lowercase p, which is the price of an item. And that's the revenue, which is this function here, minus cost. And so you'll be given a cost function, and you'll be expected to find the revenue function using this information here, and then you can find the profit. So let's look at an example of how that looks, how that works out. So here we have this situation that, again, I'll let you read just in the interest of saving time. But in this situation, this represents the price that we should sell basketball shoes based on the demand, where X is going to represent the number of shoes predicted to be sold. And so as long as we know X, we can use this equation that's given to us by this situation, and this equation is only true for this situation. This is not an equation that's true for every single problem we talk about supply and demand. So this equation will be used to find the price of shoes when we know how many shoes are to be sold. And so for our kind of first example here, so according to the demand equation, which is this one, how much should the shoes sell for if 500 pairs of shoes are sold and then 1,200 pairs of shoes? And so essentially those are my X values. So we already have the graph here, where the X value are the pairs of shoes and the Y value is the price. So in this function, I know that I need to replace X with two values. First with 500 and then evaluate it for the price, and then second with 1,200 and then evaluate that for the price. And here we can kind of easily see that from the graph. So I go over to where 500 is and I go up to my line, because this is a linear function. I can see that if we sell 500 pairs of shoes, or if that's the demand, then we should sell the shoes for $100 each. Versus if I sell 1,200 pairs of shoes, so I'm selling a lot more pairs of shoes, because the number of pairs of shoes increase, then I can lower the price a little bit for each pair of shoe. And if we don't have the graph, then algebraically, I can just substitute in those values. So if I take that 500 and I substitute it into my equation and evaluate it, that's where the $100 comes from. 500 times the slope plus the y-intercept, that gives me my $100. And subsequently, same thing is true for the 1,200 pairs of shoes. I take that information, substitute it into my equation, and evaluate it. So I can find it two ways. I can either find the information graphically using Desmos or your calculator, and then I can also substitute in the values into the equation as well. But then I want to use that information to talk about revenue for these two different prices of shoes, and then I want to talk also about how we can maximize revenue as well. And so that means we have to create different functions. So this is just the price based on the demand for the shoes. Second, revenue. We want to talk about what is the revenue if I sell 500 pairs of shoes versus 1,200 pairs of shoes. So that intuitively, we don't really need a lot of functions to figure that out. Revenue is just the money they earn. So if I can sell 500 pairs of shoes at $100 each, that's 500 times 100. And then if I can sell 1,200 pairs of shoes at $86 each, well, that's 1,200 times 86, and that'd be the revenue for 500 and 1,200 pairs of shoes. But a systemic process or a systematic process, if I look at this function, revenue is, and essentially that's what I just talked about, it is the number of items sold times its price. Well, then I can generate this function, right? X items would be 500 and 1,200, and this was the price function that we were utilizing earlier. So if I multiply those two things together, distributing this X, so X times this term and X times this term, then I end up with this quadratic function. And so now we can represent the revenue of these pairs of shoes as a quadratic function. And that will help us talk about how we can maximize revenue and maximize profit as well eventually. So to determine the revenue for 500 and 1200, well, I essentially just substitute in 500 into the value of X and evaluate it. And then I substitute 1200 into the value of X and evaluate it. So the revenue, and here's my quadratic function, that it does show the revenue, but here's my quadratic function. One where the X value is 500, so we can see it's $50,000 revenue for 500 pairs of shoes. That's at $100 each, and it's $103,200 if we sell 1,200 pairs of shoes at $86 each. And so we can evaluate that, just substituting the numbers. Now here we haven't really maximized our revenue because the maximum revenue occurs here. Somewhere between 2,000 and 3,000 pairs of shoes is the maximum revenue we can expect to get out of the shoes. And so that means the price would be much lower than $100, much lower than $86. The cheaper the item, the more we tend to sell. And then it just starts to downturn after that. So we want to figure out, this is what businesses do. They figure out how much they should sell an item for so they can get the most out of that item. And that's what we're going to do too. So part C is how many pairs of shoes should be sold in order to maximize revenue. Well, again, maximize indicates a vertex. So our vertex is somewhere around here in the graph. And that means I can utilize this formula here that we talked about previously in the notes here and also in section 4.1. So I know my vertex is going to occur somewhere around here. And because that's the vertex, then I can utilize this formula, the opposite of b divided by 2a, over my function here. So I have the value of b, 110, and then I have the value of a, negative 1 over 150. And so when I set that up, this is a numerical calculation. I can evaluate that utilizing my calculator, and that's going to give me the number of pairs of shoes that will obtain the largest revenue or the highest revenue. So 2,750 pairs of shoes. And that should make sense graphically, because if I go over to the graph, if this is where the vertex is, it's closer to 3,000. So I would expect that that number should be larger than 2,500. And now I can use that information to figure out, well, what is the maximum revenue? I still use this same function, my R of X function that we calculated, that we figured out earlier, because remember that was the number of pairs of shoes times the price. Now I essentially am doing the same thing I did with the 500 pairs of shoes and the 1,200 pairs of shoes. I'm just substituting in that value for X. So if I substitute in this value for X and evaluate it, it's going to tell me what's the most money I can achieve with these shoes. So $151,205 if we sell 2,750 pairs of shoes. And so this is the location on the function, which is my vertex. Now price, what price should we charge in order to maximize revenue? So that's using our original function, the price function, where P equaled negative 1 over 50x plus 110, and X is this many pairs of shoes. So I'm plugging that number back into my original function that we had to begin with. And so the price that I would like to charge is $55. So if I charge $55, then that is going to maximize the revenue. If I charge anything less than $55 or anything more than $55, then it becomes counterproductive and it's not going to maximize revenue. And I actually misspoke earlier. The problem I'm going to have you do in the video is going to be on page 294, where it talks about CD, so a very similar process, A through D, and it's going to have questions that pop up. For our last problem on page 296, so we skipped a few of the examples because they are more or less the same. We're looking about maximizing area, so you should have this problem on page 298 actually in your guided notebook. And I'll let you read the little background information, but there's an image of what we would hope to obtain. We have a plot of land that we want to section off or partition off for hens and roosters, and we want the areas to be equal. So we need to figure out how can we create an area function that models this situation? So I want to create an area. I want to create a function that has the most area that can contain these hens and these chickens. We want to keep them separated. So we have to think about one thing, perimeter. How do I calculate perimeter? And then how can I use that to help me get the area? So we know that in our situation that this area here is not contained, right? The chickens are not going to go swimming, so we don't need a fence there. We just need to block off this section here. And the perimeter is going to be the distance or the total fencing that we're given. We know there's 100 feet of fencing available, but we just don't know the dimensions yet. So to calculate the perimeter, P, I know that I have 3 fences that are the same length. So if I add those together, or 3 times one of them, and then there's one very, very long fence of a different length. But I know the perimeter is 100. So I know the perimeter is 100 feet. So that's one equation I can use that models the perimeter. Now, second, I also know that I can find the area based on some things that we learned in middle school. Area is going to be x times y, because it's this distance here times this distance here. Now I don't know x, I don't know y, but I can find y. I can rewrite this equation for perimeter in terms of y, and I can use that information to substitute it back into my problem. So if I were to rewrite that equation, that would give me y equals 100 minus 3x. That would be how we could find the value of y. And now I can take my area model. So the area is x times y. Well, I know y is 100 minus 3x. And so that will be 100x minus 3x squared. And so that will be a quadratic function. And that'll be for part A on that example for page 298. And then we can start answering some questions. So same questions we looked at before. It says, what should the length of the center partition be in order to maximize area? Well, here, I don't have a graph, but if we graph it, we're talking about the vertex again. And I'm gonna write down so 100x minus 3x squared. Here I'm talking about the vertex again. So that means I need to utilize x equals the negative opposite of b divided by 2a. So I know that the value of b is going to be 100. So this isn't really written in standard form, but I can rewrite it if that, hopefully it's not going to confuse you. So 3x squared plus 100. So that's typically how we would look at it. The leading coefficient is the x squared term. So the value of b is 100. The value of a is negative 3. So when I set this up, the opposite of b, so opposite of 100 divided by 2 times negative 3. So negative 100 divided by negative 6. And it's important that we pay attention to our negatives because I don't want that value to be negative because we're talking about distance here. And if we simplify that, 100 goes into 10 once, and that leaves me with what? 40, and 6 goes into 46 times, so that's 36. And that leaves me with 2/3 left over. I think it's 4/6. So that will be the length of that center partition. Now the second part says find the length of the side of the fence parallel to the river that will yield the maximum area. So that goes back to our diagram. And let me see, I can draw the diagram really quick kind of sketch. So this one is 16 feet, 16 and 2/3 feet. And now I want to find this one because that's parallel to the river. And so to do that, well, I have an equation for y that we calculated earlier on the previous screen. So this will be the length of this side here. So if I take my 16 and 2/3 or if I can keep it 100 over 6 if I wanted to, I can substitute that into here, in which actually that's, I think, what I did when I worked it out before I did the video. And then I can evaluate that. Because I know that this reduces to 2, and this is just 100 minus 50, which is 50. So 50 feet will be the length of this fencing so it can create the maximum area. And what is the maximum area? Or how do we find area? It's the length times the width, so x times y. So if I were to multiply the 16 2/3 feet by the 50 feet, then I get my maximum area that this pen can be. So 50 times 16 2/3, or probably better will be 50 will be 100 over 6. And so that's going to give me 416 2/3 feet. And so with this video, we should be ready for 4.6, which is still talking about quadratic functions, but more so applications of quadratic functions. So every single problem will be an application problem, and we have to apply the concepts we learned in 4.1, which is mainly about vertex. And so that's what we're working with.